Alabama too. So,
I worked with a guy, he was diehard. My daughter was on the Auburn at the time. I said, what if Auburn gave your son a full ride scholarship? I ain't want to go to Alabama. I said, don't take no offense to this. That's ignorant.
yeah, well, you didn't have to tell me that. You didn't.
We have to make up a while. Would be the best time.
Only if we get, only if you get it at the end of the semester, if you right. Because it don't look like we're gonna be able to do that this time, because you can't come in here and do labs when I'm not here, or somebody's not here, because this is lethal both of you. And then plus, I've already got a commitment on it, I only have office hours on Friday, you know.
That meeting off, or Friday is off the table. Is that what that means?
Right, Friday's off the table. So I get here at 8 o'clock.
So if I come in and get here at 8, I could do a lap then? Or would I
You
just
could
have to
if we'd have to put you on another trainer though, I guess. You can't have two circuits on the same trainer at the same time.
Okay, 'cause there's a few here free, I know that.
Oh
but
crap, wrong camera.
The reason I'm bringing this up to you is because I had to drive my sister's Mini Cooper to an auto shop, and I had to push it the rest of the way because it broke down. So I was a bit stressed trying to get to my house and get my car, or my other dad's car, and get here on time. So I ended up forgetting my lap of all day.
Oh yeah.
Yeah, that's why I'm like, I need to find out if I can do something to fix this kind of.
Yeah, that's the only option that we would have.
I'll do that. I'll get with you later and we can find a time, whether it's on Tuesday morning or something.
What do I have here?
They made a loader clover.
How in the world is it work?
A magnet on the bottom.
Yeah, this is a magnet here. It's actually two magnets and they're hooked on top of each other so the magnetic fields combine. Here's a power supply, but you can actually run it on like a 9-volt transistor, or we call it a 9-volt battery. You could run it on that. I'm running on my power supply. This is a 5-volt supply. Well, how's it working?
Armature got that polarity in your magnet. Which polarity? Well, the magnet don't.
Magnet can switch to there. It's a permanent magnet. So this
When
would be
that, when
this
that
would be what we call a permanent magnet motor.
when that coil goes around, it breaks north and south, well, whatever.
Yeah. So if we look at the coil real, I don't know if it'll show up, but when I turn it around, it doesn't show up real good. But this side is the insulation is stripped off of this side right here, and that side right there. You'll see it.
Yeah.
So what happens is that when it comes over here, and I'm hooking my connection to these, so these would be on a real DC motor, this would be considered what we call the brushes. And so I'm hooking my, this is metal, it's nothing but a paper clip. These things are real, this is magnetic wire. Did we talk about magnetic wire? What's the difference between regular wire and magnetic wire? So when we look inside motors, we look inside these guys right here, any motor we take apart, and we look inside these, we see that this is magnetic wire. Now what's magnetic wire? Well, this is magnetic wire. A magnetic wire is wire that has extremely thin insulation. And why do we want extremely thin insulation? So the magnetic fields will combine, right? So to get a strong magnetic field, we got to have, they call it the coefficient of coupling. How close are those wires together? The closer you can get them together, the more easier it is to combine the magnetic field. And then another thing we do to concentrate the magnetic field is we'll wire the wire around metal, right? So AC is gonna be laminated, right? You understand that term now? If it's DC, it's gonna be chunk of metal. So that's why when we look at this, the field on this one, we can see the magnetic field, we can see the magnetic wire, and then the wire is wrapped around metal. And then of course they cinch it down really, really tight. In fact, a lot of your big DC motors or big motors, they'll dip this in lacquer. Because what's happening is these wires, when you put magnetic fields, it's going to be a north and a north, and what does two like poles try to do? They repel. So they really tie them down really, 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 really tight. Like I said, a lot of times on the big motor, once they get it wound and tied down, they'll dip it down in lacquer. But this is magnetic wire, and it's really, really thin.
But that's an AC motor.
Well, I could look up at a DC motor and I would see the same thing. The only thing that difference on the DC motor is this right here would be a chunk of iron. It wouldn't be laminated. Now the rotor's going to be laminated, the armature's going to be laminated because it sees AC. We'll look at that in a minute. Okay. So, right, this is the stator of a AC motor. But if we had a DC motor stator up here, it would look almost identical except these pole pieces, but they wouldn't be laminated, they would be solid iron. Everybody understand? But it would still use what? This magnetic wire. Of course, which is the only way it could work, but it still causes problems in that if you get the insulation is so thin. Now they use a lot of it too. And the insulation is so thin, if you do get any vibration or anything rubs up against it, it's going to strip that insulation off. And then we have what we call short windings, right? Have shorted windings. Also, if they get too hot, the lamination will burn off. So I've seen people strip this stuff. They'll just take it and get a cigarette lighter and put it under there and just strip that stuff right off there. So when it gets hot, it'll come off, and of course, if it rubs, it'll come off. So you got to be careful with this. In fact, on that, all I did was get my knife and just I just scraped off the insulation on one side.
Why did you do that? Why did you strip it off?
Well, for one thing, why would you strip it off? For one thing, this orange is insulation. So anytime I terminate it, I can't crimp on something on the insulation, right? You understand? So when we put our terminals on, we would strip it off. Okay. Inside here though, we don't want to strip it off.
I thought you were talking about stripping inside.
Well, I had to strip this off right here because I had to make, but only on one side. If I'd have stripped it on both sides, I would have a short circuit, right? You understand that? So what happens is that when it spins, this guy here don't have a magnetic field on it, but it's got what we call kinetic motion. Anything that's in motion wants to do stay in motion. So as long as it overcomes friction, it will spin around. And then when it gets right about here, it picks up. Now it's on that conductor, and now it conducts, creates a magnetic field, causes it to swing through, and then it gets enough kinetic energy to do what? Swing around. So to do a DC motor, we've got to have this. First of all, a DC motor, the rotor or the armature. So the correct name, by the way, for a DC, for this rotating part, the technical name is that they call it the armature. But you hear a lot of people call it the rotor, but it's not. It's an armature. And then we come over here and hook this up. Of course, I don't have enough to cause it to spin. So on this one, I have to start it. Supposedly. I know what's going on. Hold on. I usually take the brushes down. But then once it's started, it should do what? Yeah. No, perpetual motion is something that, which there's no real thing is perpetual energy, right? What's the perpetual energy supposedly? Or the the energy used is equal to the energy you use is equal to the energy you put in.
You're not accounting for loss.
Right, you don't have, it would be a system that has zero loss. There's no such thing. We had a guy that came in and he got this big bright idea. He had all these tractors, forklifts at his plant, where he worked. It wasn't a plant, it was a warehouse. And he said, I'm gonna put generators on the wheels, so when they're driving the forklift, it'll charge the batteries. And I told him, well, it's gonna run down faster. Right, you understand why? I said, your batteries will run down faster. Now vehicles do that, but they do it, they only charge the batteries when like the car is going downhill, right? So they're using the gravity to give you the energy. But there's no such thing as 100% efficient. Yeah, battery powered forklifts. You know, a lot of forklifts that are used indoors, and a lot of times they use batteries. Or most of them now use propane because it's a really, really clean burning fuel. But for years, if it was in a warehouse or a steel warehouse that had very little insulation, they would use batteries. Of course, they would do what? They would charge it up. So this is a good little science project. You know, if you got kids, very, very easy to do. Like I said, you could run it on a 9-volt battery. It would run fine. I'm running off 5 volts. I'm running off a power supply. If I increase the voltage, the speed of the motor should go up until it meets its limits. So you got friction, and when all this stuff matches out, then the motor would run at a certain speed. In fact, the way a DC motor works, a DC motor works on what we call counter EMF. So what happens is we have a bunch of wire. How much resistance does wire have to DC? What determines the resistance a wire has? Well, we say the size, but technically what we say in electronics is we say the gauge, the length. Well, not really the insulation, but there's a byproduct of insulation that causes it to have a resistance. The material it's made out of. What's the best conductor of electricity? Best known conductor of electricity? Yeah, silver. What's next? Yeah, copper. What's next? Gold. And then what's next? And which are the most two used? Now, these are the two most often used. We use silver as a plating. Just about all your relay contacts are silver plated. And then we use gold. What advantage does gold have over these other metals? Well, it does, but it oxidizes so slow we'd probably all be dead before it does. Yeah, it's too expensive. So we use gold as a plating too. A lot of times in the old days, if you had any printed circuit boards, anything that was going to be exposed to the atmosphere had a gold plating. And that's still true. Most computers don't use gold anymore, they use tin. Because they think tin has a very low oxidation rate, but it does oxidize. But what happens is that by the time it oxidizes in a computer, the computer is basically obsolete.
You get you an electronics store, you buy the cable, TV, audio cable. It would have gold on it, but you really don't need it there.
Well, sometimes those are the high quality cables. If you're going to mount them where you can't get to them, because if you get the regular tin plated cables, you're going to have to twist them a little bit every once in a while just to keep them. Especially if you're in stereo. The problem with turntables and stuff like that is the voltage coming out of those things is so dang low that if you got any resistance in there at all, so, turntables and, stuff like that, that's where we'd usually use those, but I never did because I just twist them every once in a while. So let's look and see, a DC motor. Let me find out. This guy's, good on some things, but then other things he's not. Uh,
universal motor. In this video, I'll explain how they work. So here's my Ryobi hand drill, and in the front we got the chuck and some gears. And these are driven by the rotor, which fits inside the stator.
when it's on, in fact, I should stop it and just upload the video. Find the link back to the video. This guy uses some terms that are not quite correct. It's okay. Yeah, and that's what I'm saying. A lot of people do that. Technically, it's not good. So what we're doing is you look. So this is the armature of a typical DC motor. Whether it's a series motor or a shunt motor or a compound motor. So instead of me scraping off frames, you see this thing in the back, it's the way it's slotted. We refer to that as the commutator. And what this does is it passes the electrical current from a stationary part. The motor frame and everything is stationary. And the rotor is rotating. Well, we got to put that magnetic field, the electromagnet, it's got to go into the rotor. And it's got to be switched, right? So what we have to do to make a motor turn is one of the fields has got to rotate. Well, how can we rotate it with a DC motor? I mean, we can do it with AC and three-phase really big because it creates a field. But DC don't change. So what do? Well, we use the motor itself to constantly do what? Constantly change the current, which causes the motor to do what? Turn itself, right? Does that make sense? And this guy does a really, really good job of demonstrating. But we have to transfer the energy from the stationary part over to that commutator so it can be switched, so the motor will rotate. So we have brushes on there, and we'll show y'all some of those probably not on the motors that we play around with there. They have brushes, which are carbon brushes that basically have a wire embedded in them, and they transfer the energy from the power source into the armature. Of course, so one of the biggest advantages of DC motors is they take preventative maintenance. You won't want to lie. So eventually those brushes are going to live on. You got brushes in your alternator because they have a spinning magnetic field. They don't have a commutator because we don't want to change that polarity. But usually when the alternator goes out, and it will eventually go out, the problem is what? Use those brushes on the problem. You go out and pay $150 and send it down to Kansas down in Desper and they replace the brush, clean it up real good and shut it out. Starter instead of that much. So starting your car, all your motors inside your car are DC motors. Right? So if you used to take any of those, the one that's running your wipers, the one that's running your fan, the one that's running your radiator, most cars now, used to we had belt near the fans that cool the radiator. Now we run electric fans because they can control it a lot better. So a motor is more efficient when it's hot. So you look out there, that fan, when you first crank your car, that fan don't do what? It don't turn on. And then when you stop, a lot of times what happens? The fan keeps going, right, through that radiator. So we got brushes we got to clean up. We got commentators. You can see this is starting to get worn. So that we have to furnish and then rubber. So when I first put power on this thing, all the resistance we have of the armature is the resistance of the wire. So what would be the inrush current into the armature? Would it be high or would it be low? Yeah, it's going to be very high, right? And this is why these motors, but we want it to be high because what determines the amount of torque the motor produces? That's exactly right. Well, sort of. What determines the amount of torque a motor produces is the strength, the interaction of the magnetic field. The more current you have flowing into the electromagnet, the stronger the field. Right? You understand? So this creates, you have all this current that rushes into that armature. It creates an extremely strong magnetic field. Then you have another field out here that's fixed. It don't rotate. In fact, that's what we call that. We call that the field. He's going to call it the stator, but we call that the field. And that guy don't change, so it's got basically the same current all the time. We're going to start off with it. It's an electromagnet. But it's a stationary field. So it could be one of two things. It could be an electromagnet or it could be a what? It could be a permanent magnet. So just about every little motor in your car is a permanent magnet motor. The field is permanent magnets, right? You understand? And then we switch the road. I mean, not the road, you know what I'm saying. But what happens is that, so what's required to produce a EMF using magnetics? First of all, we got to have a watt. We got to have a magnetic field. 2, we got to have a watt. 3, we have to have a watt. Understand that. What determines the amount? Number of conductor loops. Or windings. And then number 3, the watt. So that means all I need to do, I know it's not, but all that I need to do, all I need to do, what do I have here? Okay, what do I have here? Okay. What do I have here? I don't have nothing. I don't have nothing. We don't have motion. As soon as I have motion, now I'm spinning it. What type of current am I making? Okay, now you understand how I'm going. That's what I do. Except, they don't have our power. This is an electromagnet. DC on this. So you don't want to take the power off something that's heated, right? And that's a big problem. DC generators have, and that's why we don't have the cars. So I put DC on this, and put brushes into it, that's spinning the magnetic field, and then we just the voltage into the stationary state. That's what the car does. What advantage is electromagnet have that permanent? Yeah, we can control the circuit. So that's what your car, that's what your regulators do. It's monitoring the output on the draw alternator, DC. And if it tries to drop down, they put more strength in the field, more current in the field. If it tries to go up, they do what? Take it away. And that's the way, now you know how regulators work. Alabama Power does the same thing. It's up there at 18. So what happens when I've got this coil wire? So we got to have at least 2 commutator pieces. They'll follow this, and then we'll come up, and then we'll have the loop. And then what we have on here, right, you understand that? Yes or no? Okay. Gotta have at least two. The more slots slots they have on the commutator, the smoother the motor runs. So instead of switching every 90 degrees or 180 degrees, you might switch it a lot, right? You understand? It makes the motor run a lot smoother and make a lot of torque. This one right here, you see it bumps like that, right? Because we've only got one slot in our commutator. So I've got this magnetic field out here. It can be permanent or it can be fixed. Now this guy right here is going to spin into a magnetic field. So what's it going to do? What's it going to do into the armature? If this wire is spinning, it's a magnetic field. What's it going to do? It's going to induce a voltage back into the armature. This voltage that is induced back into the armature would be, so if my applied current is trying to push voltage in current this direction, then the counter EMF does what? Pushes it in the opposite direction. That's the way it's running. And what happens is the effective voltage on the armature. So if I put 10 volts on my armature and it creates 2 volts of counter EMF, the effective voltage would be what? 8 volts. The motor speed comes up. Now I'm getting 3 volts. I'm not changing my voltage over here. So now the effective voltage on the armature would be 7 volts. 4 volts, 6 volts, right? So as the speed of the motor comes up, the effective voltage that the armature sees goes down. Until when? Well, it can't ever hit 0, because if it ever hits 0, then the motor would stop. But so it pulls enough current, it runs at a speed. It creates a counter EMF that's required to develop that horsepower. Y'all understand that? So the counter EMF will never, ever be 0. But when does the motor require the less? When does it require the less power or the less torque? When it's at speed, right? You understand? What's it doing at speed? So when it's setting at rest, it's trying to start something else at its rest. So when we start the DC motor, it creates tons of torque, right? You understand? It starts that thing running. And then what do? Then we don't need all that power. We don't need all that current. All we got to do is run the water. Got to run the load. And plus the friction. That's the way DC motors work. So watch this guy. This is a really neat video. The way he does it. I've got a little armature that I'm working on. That I'm going to try to do this with.
On one side for cooling, and then here we've got layers of laminated iron with copper windings in between, which are connected.
Now, why, if this is DC, why is the armature laminated? Because it's seeing a fluctuating DC, right? I mean, it's seeing AC basically, because it's constantly being switched. So we have to laminate the core of the armature.
So the individual piece of copper on the commutator. On both ends of the shaft, we have a ball bearing, and I'm just going to put this in this block of wood here, and I'll hold that with the clamp. The windings in here and the iron core essentially form an electromagnet. They're wired up to the commutator in such a way that if I apply electricity from here to here, the north and south poles here will be here and here. So let me demonstrate by applying a little bit of current. Like so, and now I'll hold a compass on here. And you can see there's one pole here, and the other side has got the south pole pointing at it. And now the cool thing is if I move these around somewhere else, the north pole here is always going to be pointing to whichever side I'm applying that wire to. The thing with magnets is that north and south are always attracted to each other. So this magnet is trying to orient itself with the south pole facing north, because north is this way here. So now if I bring the south pole of another magnet nearby, that wants to reorient itself. And so if I bring it in from the side, whichever direction, it's always the north and south are attracted to each other. So if I have a magnet like this, and I bring this magnet in like so, it wants to rotate this way. This rotor forms an electromagnet, and if I apply just a little bit of current, in this case from a AA battery, and I put some leads on with a rubber band, and I apply current here, it's got the north and south poles here and here, and now if I bring a magnet in from the side, it always tries to orient itself towards that. And you notice now it's spinning. So the cool trick is, the north and south poles will always be this way, and with the magnet here, it tries to orient itself this way, but as soon as it reorients itself, we're connected to different contacts on the commutator, so north and south will still be this way, and so the rotation just is continuous. But as a motor, this is actually very ineffective because magnetic flux travels about 1,000 times better through magnets and through an iron core in here than it does through the air. And if I hold this near, I'm not really getting that much magnetic flux through here. If I get too near, it just gets stuck. To give the flux a better path, I devised this thing here where I've got this bent piece of iron, and I've got two rare earth magnets here and here. And now if I put the rotor in between, can have a much smaller air gap, although it's still pretty large for a motor, and the flux can then go around here, so I'll get much more flux going through everything. So let's apply the AA battery again. This time I have to go top and bottom because my magnetic poles are on the sides. You can see it spins, but not terribly fast. Part of this is this rotor is actually made for a 110 volt motor, and I'm only applying 1.5 volts here. Partially what's limiting the speed of rotation here is that as this spins, it generates a reverse voltage just from the changing magnetic field going through the coils. So with this homemade voltmeter set to 1 volt full scale, I now put the contacts here and I spin this. You can see I get a voltage here, and I can easily get up to about 0.6 volts. And that 0.6 volts works against the battery's own voltage, so it's cut down on how much current I can get through. So now back to the power supply and 3 volts on my wires. Let's see how that goes. So that already spins a lot faster, but let's turn this up, and now we're at about 30 volts out here. And let's try that.
Yeah, so that's what they want to stand in, that balance.
Again. Now that seems pretty fast, but in an actual drill, this rotor would be spinning 100 to 200 times per second. How powerful a motor actually is a function of how strong this magnet is and how strong the magnets on the outside are. And this is just a very crude setup. In an actual drill, the magnet around it is very close and much stronger. With the flux being able to go through iron about 1,000 times more easily than through air, there's a very small gap around the rotor so that we have a lot of flux going through here. Now what I was explaining is how this works as a DC motor, but this is actually a universal motor and it runs on AC. And the way that works is the stator, rather than having permanent magnets in it, actually has electromagnets as well. So with the AC reversing direction 60 times per second, if we had permanent magnets, it would just want to wiggle back and forth 60 times per second, but that's no good at all. But because
So what do you call this motor? Universal motor, which means what? Yeah, we can write it on AC and DC, and we'll look at that in a second. We'll kind of simulate a universal motor back there. So what happens is that you're constantly changing polarities here, right? You understand? But you're constantly changing polarities here too. And they're changing at the same rate.
field magnets,
So let's come back here. So back there, when I swapped it like this, what did you do? Did nothing. Okay. So why can't I put AC on that thing? It runs in the same direction. No, I'm talking about back there. There's no problem. If I put AC on it, why can't I run that motor on AC? What we got is all we've got in the armature is the resistance of the wire. Everybody understand that? Now, if I put DC on that thing, then it never changes. It never, the field never changes direction. So the field, to get a big R on the field, we got to use a lot of terms to find gauge wire. Now we end up with a formula. So the amount of a wire, the amount of when we talk about what determines the resistance of a wire, we say, what's the three things? The gauge, the material, and the length, right? And then what's the third one? So Thomas said the insulation, it's not the insulation that's causing the resistance, it's the temperature that can't get out of the conductor because it's what? Because it's insulated. You understand that? So the insulation doesn't change the resistance, it's the temperature of the wire. So it's just like in the wintertime, what do y'all usually do? What do you usually wear? You wear a coat, right? And what does that do? It keeps that heat from doing what? Escaping. It keeps your body heat from escaping. To keep the coat don't create heat. If you're sitting there at 98.6 degrees, right, you understand if you insulate that, then that temperature stays in. If you come up and get out of that, you expose the skin to air, then what's it going to do? It's going to get rid of heat, right? You understand that? So if you went out there and put on a big old thick coat right now, what would happen? You'd get very hot. To get that though, every time we have a coil of wire, when I put AC on a coil of wire, then what happens is when AC tries to go up, it comes up here and it creates a magnetic field. It induces a voltage into the next wire. But it's going to try to buck the voltage that was produced there. So when I put AC on a coil of wire, it creates another opposition that we call inductive reaction, the opposition to AC. So this is how much inductance it has. So this is the problem we have with running a regular DC motor on AC, is that the field would have no current flow in it at all. You understand that? So it would run because the X of L would be so high. But we got a bunch of terms of wire, so we don't burn it up on what? DC. So if I put AC on the motor, it wouldn't do anything. Well, it might give you problems with the armature. The armature has low X of L anyway, because it does see X, right? You understand that? But the field would not create any magnetic field, so the motor would start. Are y'all following? Okay, now y'all take a break. 2 minutes. Yeah, I need to go ahead and do row. We only had 450. people here to start class. So 4:30, I think, is the one you were looking at. Oh, dang it. Okay, guys, y'all look up. Yep. Been 10 minutes, whether people's in here or not. So we've got several ways we can buy these motors. By the way, this is the symbol for the armature. Kind of looks like a, so they show the brushes. That's the standard symbol that we use there. So this is one way we can have it. This is called a shunt motor. So a term we call, we use a term every once in a while called shunt, and it uses in parallel, right? And then we have another way we can do it. This is called a separately excited motor. Now, one thing, the shunt motor usually is non-reversible. Separate excited is reversible, right? And you can control both the field and control both the armature. If you increase the voltage on the field, the motor will slow down because it produces a stronger magnetic field, which will produce more counter EMF in the armature. The motor slows down. If you lower the voltage on the field without changing the voltage on the armature, the motor will speed up. So the problem is playing around in the field, the motor's up and running, and you reset the field, the motor could run away just from the residual magnetism of the pole pieces. So those magnetic pole pieces on a DC motor are they're solid chunks of iron, right? You understand? What happens when you put magnets, solid chunks of iron together? They magnetize, right? So that means what would happen on a shunt motor, lost the field, and the motor was up and running, and he could literally run away and swing himself apart. So we don't like to fool with the field. But normally we could change the voltage on the field and raise the voltage. The torque of the motor would go up and the speed of the motor would go down. So we could use the field to control the torque. The problem is that the motor speed is going to vary opposite the field, right? You understand that? So a separately excited motor can leave the field voltage on the time. We can do all types of neat stuff with that, and it's very easy to reverse. Normally we reverse the what? The armature, right? Then we have this guy. Now what's nice about a shunt motor is that the field voltages don't change. And of course the polarity don't make any difference. The motor's going to run in a direction, right? No matter how you put those up. So what would happen if the motor tried to slow down? Well, if the motor tried to slow down, its opposition would go down, its current would go up, its torque would go up, and the motor would try to speed back up. So what's nice about a shunt motor, it has really good speed characteristics. So this guy tries to run at a constant speed. Because if the rotor tries to go down, it tries to slow down, what's going to happen? Counter EMF goes down, it pulls more current, its magnetic field goes up, and we'll try to cause the motor to do what? Speed back up. So shunt motors have really good. The advantage of a separately excited motor is that we can reverse it really by reversing the armature, not magnetic. Right? A second advantage it has is that we can control both of them. Understand that? So if I want more torque, I can increase both of the fields. If I want more speed, I can increase the torque of both of them. It's easy to reverse. Then we have what we call a series motor. Now what's nice about a series motor is that these guys field and the armature are in series with each other. So what happens if you put this sucker in a very hard load, you try to make the motor slow down, the motor slows down, the counter F goes down, the resistance of the armature goes down, the current in the armature goes up, the current in the armature and the field are here. So what happens is the current in the field goes up. So now we got big, strong magnetic fields and they interact with each other, right? So what happens with this guy, if you put this thing into a load, it's going to slow down, but it's going to create a bunch of torque. This is what's in your drills. You ever had some of your drills get power? What does that drill do? It'll rip itself right out of your hand, right? Because it's a series motor. Now what's nice about a series motor is that dang series field has almost no X of L at all. It's a very small inductor. And of course, how much opposition it has to AC is equal to 2 pi FL. Well, if L is real small, then what can we put on this thing, We can put an F on this thing. We can put a frequency on this thing. So series motors are also referred to as universal motors. Oops, got wrong. Which means series motors can run on water. That's it. So remember, if it swaps, it's not going to change direction. How do you change it? When you take that thing on the side of your drill and flip that switch, you're changing the armature, right? Connection. And then the last type of motor we have is what we call a compound motor. What do you think a compound motor would do? Yeah, a compound motor is a series motor and a field. Now this series motor is real simple. I'll have to look it up myself. But so this guy right here has great torque, right? And this is force speed. These guys here have very force speed. As soon as you go out there and you load your hand drill down, what is it? Slow down. So what happens to the torque? It goes up. Yeah. Shunt motors have poor torque characteristics, but they have real good speed characteristics. So what happens on a cumulative or a compound motor is that you get both features. So you get good speed regulation and it's great and good torque, right? You understand that? So the speed regulation is not as good as a shunt motor, and the torque is not as good as a series motor, but you get both features. And we have what we call a cumulative compound and a differential compound. I can't remember, I need to look that up, but one of them is better on speed, and one of them is better on torque. And all they do is they change the way they do the speed. But all these motors, what's the way to reverse it? But engine standard. Armature. Now this would be the armature right here, so this would be that. You leave this guy alone, you reverse it. Alright, understand that. And we got one more motor. They usually draw it like this. EM motor. You know what that stands for? Yeah, permanent magnet. And these are used in very low torque applications, very low power applications, very low speed applications. So sometimes we have to use it, right? You see that every motor in your car is a permanent magnet. You got a windshield washer, and there's one on the other control, blowers for your air conditioner cooling system. Right? You got an antenna that electric antenna, you got one on there. So you can probably keep these notice in your car. Somebody told me the average time. So compound motors, these have fair speed characteristics, fair force characteristics. Speed characteristics is not as good as the shunt, and the torque is not as good as that series. These are the guys that's used a lot, especially me. Because what I can do is I can play around with both of it, right? Most of the motors out of US Steel are compound motors. And normally, how do we change the speed? Well, normally we change the speed by changing the voltage a lot. And it varies in the same direction. So if you raise the voltage, the speed goes up. If you lower the voltage, the speed goes up. Pretty straightforward. And for years and years and years, these were the guys for speed control. These were the guys. Now, since we got the development of solid state devices, AC motors is probably the dominant speed control over now. What advantages does an AC motor have over a DC motor? Yeah, they don't have a wound rotor. They don't have all that copper in the rotor. You don't have any rotor. It works off induction. Induction motors work off together. So AC motors are a lot cheaper for horsepower. So a brushless DC motor is really, really good. And we can put that up there, by the way. But, what they do on a brushless DC motor is they have a bunch of field wires. And these are electronically controlled motors. And then in the center, what we have a permanent magnet. Electronically, they do a spin field. And that's a brushless DC motor. So all your motors inside the control and the brushless because we don't want to monitor that inside. Another disadvantage DC motors have is they generate a bunch of electromagnetic interference. The first way they transmit data is what they call a spark gap transfer. And when you create that spark, I don't know if y'all remember originally in cars, if you had regular cars, you could hardly listen because they hooked up all the car parts. The little car parts out there just transmit. So all the guys who got special wiring, resistance wiring, that reduces the initial R. It has to come through to reduce the initial R. You don't want to wire spark plugs with regular wires because the radio will pick that up. So DC motors, when that commutator spins, generate all types of R's for hard equipment. So I can't put those type motors inside of the PC. So then you keep electronically controlled brushless motor. Works kind of like a stepping motor, but a stepping motor, the field moves in steps, right? Just the field rotates so fast. And the magnet is kind of weird, it's like a taxi because circular magnet that goes all the way around the car of the road. So it's constantly moving against the field. So it don't move in steps. Kind of like running a stepping motor in what we call slew mode, where you rotate it so fast it appears to be going. That's a constant mode. Stepping motor, we call it slew mode. So that's basically what we've got. Well, they're both precise. You gotta have feedback. Normally, what a Russian DC motor has to have, it'll have a Hall effect sensor in it that's on the spinning magnet, and then it sends that to the electronics to rotate the regulator setting. If it did the same thing with the DC motor, yeah, we can control the DC motor down to, I'm not going to control the DC motor. You can control DC motors precise. It's just that these don't generate any noise. Extremely low torque. But what they have to do, like steam fans inside your computer and run hard drive, those things don't get any torque anyway, right? So yeah. So we do have another one. This guy's called brushless DC motor. And then we have stepper motors too. This guy in the stepper motor is a lot alike. But on the stepper motor, instead of spinning the field real fast, we have to literally do energize one at a time. And the motor moves the steel. And then the alignment of these fields and how many magnets you have there gives you an extremely precise step size. And we're talking, it depends on how many magnets you have in there. So like a 24 magnet, you take the 360 divided by 24, and that would be 3 per step. I don't know which one's really, how many steps? Yeah, but how many steps? You can count the steps per revolution, and then you can multiply that and divide that into 360, and that will tell you. So you can take the step size and multiply it times 360, and that'll tell you how many poles you have in there. So you'll have to do it backwards. So we do have some motors that we don't do. So stepper motors and brushless DC motors, these are controlled by electronics. These guys up here, we can control these three. Plus, it's what we're doing in this class. We're calling. You're getting what we call a degree per step. So if it's a 24-step motor, and what they do is the field, the stator, or the field out here, these fields are aligned exactly precisely. So if you have 24 steps, then we would come up here, and how many degrees in a revolution? 360, and then we divide it by the number of steps. And this would give us degrees per step. So Leslie said his is about 1.3 something degrees per step. Leslie, by the way, makes 3D printers, shrink printers. So, and he uses 7 motors. That's how precise these motors are. And they're open loop because they're so precise. All you have to do is let them find themselves one time. So you find themselves one time, you come up with what we call an origin, find it one time, and then from then on you can precisely control the step, as long as something not spoiled or solid. Yeah, if you wanted to find the number of steps, you can take 360 and multiply it. You divide it by 1.35, and that will tell you the number of steps. We got some over there that step size extremely small. I don't know why you're not going to deal with stepper motors. The stepper motors are really, really neat because we can run them open loop. Y'all know what open loop means? Without feedback. Yeah, so odds are your printers, if you got documented printers at your house, odds are you can watch stepper motors. Advance the paper, that's why you hear this when paper pulls through there, that's stepper motor. And so that means it only picks up the front of the top of the page. You got a sensor that picks up the top of the page, but it seems to print at the same place every time. So once it sees the top of the page, it knows it steps so many steps, and now you're ready to print it. So we run these stepper motors all over. Very precise, and we can run them open loop, even though they do closed loop on robots. Some robots use stepper motors, and they run those closed loop. So you can run them even open loop or closed loop. In fact, you can buy stepper motors with encoders built into them. So change the direction of the field, right? Change the direction of the what? Armature. Okay, so how does AC motors work? I'll throw that time, guys. I don't know. How does AC motors work? Well, what we do on an AC motor, the main motors we use out there and the cheapest are called induction motors. So what do you think these things work off? Yeah, they work like transformers. In fact, that's what they are, transformers. And short and secondary. So if you look at the rotor on an induction motor, these are the They're not painted over. Sometimes they paint these things over. Dang it, I don't know what happened. I don't know why it does that. But what we would do, if you look at this thing, is we'd see a bunch of laminated plates. But if we stripped off the laminated plates, what we'd see is these conductors. You can see these very well. And then on the end, they have shorting rings. Now, to concentrate the magnetic field, what are they embedded in? Well, they're embedded in laminated plates, right? You understand? And they're shorted on each end. I mean, you can see it as plain as day. Instead of me putting it on the camera, I'll just pass it around. So these little aluminum bars you see running through there, that's what it does. So if I come over here and put AC on this thing, then the AC is going to come up. It's going to induce a voltage into that. It's shorted out, so that means it's going to start off pulling tons of current. It's going to create a real strong magnetic field. It's going to create a lot of current in your stator, the field line, because it's got a high current on the secondary side. You understand that? It's going to create a lot of torque, and the motor's going to start to spin. If the field spins, y'all understand that? But if I come up here and do that, then when this is a north, this might be a south. When this is a south, this would be a north. What would it do? It just sit there, right? You understand? No, it ain't gonna turn. It's just gonna sit there, unless I do what? Well, I'm not changing polarity there. What I have to do here, how does the DC motor work? Well, we constantly cause the magnetic field to move, right? You understand that? So what I'd have to do is I'd have to have a second, so on an AC motor, I gotta have a second set of windings. I'm going to draw the rotor like this. So I'd have to have a what? A second set of windings. And what would we have to have? Well, if I came over here and this was a north, and this was a south, and this was a north, and this was a south. I'm sorry, I got that wrong. This would be a north, this would be a south, this would be a south, this would be a north. What would happen? Well, the rotor wouldn't move. Because when this south would induce a north, and it's going to lock in, this north would induce a what? A south. This north would induce a south, and this would do, and the thing would just sit there and hum it. Right? You understand? So what we got to do is we got to make a magnetic field move. Now, which is going to move? Well, this guy right here can't move right now because it's stationary, right? You understand that? So what do we got to do is we got to cause a phase shift in these fields out here. What do we mean by phase shift? Well, when one's dropping down, the other one needs to be doing what? Coming up. Y'all understand that? Well, three-phase we have no problem because three-phase, we got a phase we call A. It looks like this. And then 120 electrical degrees out, we got another phase that's starting right here, and it's doing the same thing. And then 120 electrical degrees after that one, the other phase comes in, and this is constantly repeating. So if I call this guy right here A, and I call this B, and call this C, then what's going to happen? Well, first of all, we'll have to have a bunch of fields. So we'd have to have one pole for each field. They're going to be all set for about 120 degrees. And so what would happen is this right here would be A, and this over here would be A. This right over here might be B, and this right over here would be B. This might be C, and that would be C. Y'all understand? Yes or no? So what happens, A builds up, and when A starts dropping down, what happens? B builds up, which causes the field to do what? Shift. Okay, and then when B starts dropping down, C builds up, and then now it goes to the negative polarity, and we pick up A, so these guys are going to swap now, and it's going to do what? spin, and then what's it gonna do? So three-phase motors, they come up and spin automatically. This is single-phase motors we got problems. So three-phase automatically generates a rotating field. Yeah, it's more efficient. Motors are more efficient because you drive a rotating field all the time. It's pulling and pushing that motor around there, right? So that means if I've got a big old company that needs a lot of power, my motors are going to be three-phase. But in my house, it would be a lot more efficient for me. How many have multiple phases in your house? Nobody has multiple phases. Unless you're very rich. You got a big old house. So we got to figure out a way that we can power the most of those correctly. Now to do this, we got two devices that I showed y'all at the first semester that create phase shifts. What are those? Capacitors and inductors. Inductors are a little different because the field is inductive, but if I could make this one have a lot bigger L than that one right there, then we would get a phase shift. So we got two types of single phase motors. So we have capacitive, and we have what they call split phase. Split phase uses the high inductance winding to cause phase shift, so it's inductive, capacitive. Now capacitors are more expensive. Capacitive motors are more expensive, but they can create more starting torque. They got better torque. Split phase motors are very, very cheap, but they have very poor torque. You got a single phase motor and you don't see capacitors on them, and it's probably a lot of split phase. Split phase motors are used on a lot of devices that has lower starting torque than it has run torque. What do we use that has low starting torque and high run torque? I think, yeah, split phase motors are used on a lot of things. Because it creates its torque when the thing is at the number, right? Capacitive motors, we have two types. We have capacitive start and we have capacitive run. The problem is so all we need is that phase shift. The more that your start winding, so we have two windings on the single phase motor. We have what we call a start winding and we have what we call a run winding. Once something's in motion, it wants to stay in motion. So it means I can use very cheap start windings, but if I left them in the circuit all the time, they would burn up. You understand that? So what we do is they'll have these motors will have what we call a centrifugal switch on them. What they'll do is when you throw power on them, the start winding will be switched in. As soon as it starts running, it'll be on. Check it out. You hear these guys click all the time. When you start it. And then when they slow down and stop, you'll feel another click. And that's going to be your start line. We have another one where it has two capacitors. It kicks in both of them to start it, and then it kicks out one of them when it gets up to speed. Now these motors have two capacitors. We call these capacitive run motors, even though we still start them capacitors, right? Now these motors, they create more torque for a smaller size, but they cost a lot more money. So about the only time you'll see a capacitive run motor is an application with the size is critical. So they cost a lot more money. There's a lot of applications where the size is critical. So, and that's what these guys are. So this guy right here, this guy, most of your fans, most of your motors use the SPS system. Using external start instead of putting it on the motor, they actually put the ground wires just past it. That's pretty standard program. I don't remember the color. All I remember is the yellow is common, and then these other three wires. Could be a low, yeah, lower. It wouldn't all that outside. Yeah, this would be outside. Well, normally what the blower on your air conditioner runs at least 2 speeds. Hot air is easier to move than cold. So, plus cold air is good. So that means to get it to blow your air conditioner, it's got to run at 1 speed, a higher speed, and the heat is a low speed. This is the blower motor off an HVAC. This is a standard blower motor off an HVAC. It's going out before, but it's going there. Yeah. It's a dual purpose unit, combo unit, not a combo unit. So it's got both heat and air conditioning in one unit. And that's why it's got the work for it. So they usually only use 2 speeds. They usually only use 2 speeds. They use medium and high. They use high for air conditioning and medium for this, and they don't usually use low speed. This is the only way you buy it, so you can have speed motors as far as that. Now what they do on this one, what sets the speed on an AC motor? Just talked about it last class, right? RPM equals 120 times the frequency divided by the number of poles minus the slip. That's how fast the motor runs. So we got 2 ways we can primarily control the speed. That's by changing the what? The number of poles. Or changing, no, not an AC motor. We don't screw around with voltage on an AC motor. A motor drive, we have AC coming in, and then we have a drive, and this is electronics, and then we have a motor. And now the problem is, for years, this was a what type of motor? A DC motor. So if I want to control it, so when they came out, when the electronics got good enough for them to play around with this, then we still have AC, then we come in and we change the AC, but we still have a what? We still have a drive, and now we have a motor. Still have a motor. Right? You understand that? So this is why AC is dominating the motors now, because why? The drives are about the same cost. AC coming in, but what? I had a pump on my pool. So what happens if we take out the start capacitor? We didn't do that. Let me go do that. Yeah, we'll take out the start capacitor. Yeah, let's remove the start capacitor. So the start capacitor is the start line. That's one way you can tell the start capacitor out in the motor, and it's not running no matter what direction. So industry standard for reversing a single phase motor is to do what? Reverse. If the start winding don't come up, you can't change the motor. There's a lot of single phase motors that are not designed to be reversed. This guy right here is not designed to be reversed. It runs the fan, right? You understand that? So if they don't bring that start line out, then there's no way more you can do it. So brown and brown is the start capacitor. White or yellow is common. And black is high, blue is medium, and green is low. They're changing the name of the color, just like you do your cinnamon. That's exactly what you do. So how do we change the three-phase motor? This is the last thing we'll look at. Yeah. There's no start winding on three-phase motor. Three-phase motors, we don't have to create a phase shift in a three-phase motor because why? Because it creates a rotating field. Well, what we got to do is make it rotate in the opposite direction. If I swap all three of them, it's not going to do anything, right? So I need to swap two. So which one do we normally stop? So we call it phase A, B, C. And we got going A. Right, A, B, C. A, B, C. The industry standard is to swap L1 and L3. And leave L2 alone. So let's should you hook those up? Well, originally, and then if you do it according to industry standards, you're supposed to swap industry standard. But you're right. I wanted to, but it's not supposed to do that, especially so what we're going to fix to do is fix to go to the lab. What we'll do later on, so what I want to tell you, the circuit that reverses these motors are the same, whether they're DC motor, AC motor, that reversing circuit. The circuits themselves are identical, whether it's single phase, multi-phase, whether it's AC, DC, it makes no difference on the control circuit. What makes the difference is how you wire the contacts for the relay, right? You understand? But the reversing circuit on these motors are all the same. Y'all understand? Because all you're doing is normally we have two relays. One we're going to call what? Forward. One we're going to call what? Reserve. We're going to interlock them so they can't come in at the same time. Because if I swap these leads, right, you understand. If I forward and reverse, so one of them's going to have a start line this way, and one of them's going to have it this way. And if I let the forward and reverse relay come at the same time, you got what we call a bridge circuit on this now. So we're going to interlock these things. Which means that we're going to interlock it so they can't what? They can't come in at the same time. Even if you screw it up, they can't come in. You're going to look how to do that. The reversing circuits themselves are the same. Y'all understand that? So, AC now what was happening was the fixed AC, the variable AC look, there's a little light on the plug, and you plug in 120 volts, and it'll power. So imagine that 120 volt output over there is connected in parallel with that output. But the variable single phase work fine. So what I had to do is I had to wire it directly into the output of the grid. And we've had that happen on circuit. So any more questions? So the circuit that reverses a motor is going to be basically the same for all motors. Yeah, what we want to do is, y'all can do this one. I'd like everybody to work on this right today. Is everybody here? Who's your lab partner? Michael's not here. First of all, who came in late? Nobody came in and told me. Oh, Frank Lavana told me they was here. He was here. Huh? Everybody wasn't on time. When class started, there's 2 people in here now. I think Barry told me he read it. Huh? Okay, so let's come over here to the motor.